The octoScope throughput script works with a pair of devices, an access point and a client. The device under test is placed in the upper chamber on a turntable, allowing for examination of performance relative to device orientation. The reference device, in this case an access point, is connected via coax in the lower chamber. In between the two chambers we have a broadband multipath emulator. The RF signal is coupled from the access point to the lower chamber through the multipath emulator to the device under test in the top chamber. To simplify the connections required, we radiate over the air to the device under test. Once device connectivity is confirmed, automated measurements are made. The octoScope throughput script controls the device orientation, the path loss between the devices under test, any interference we may want to introduce, and the traffic generation source. This is what a typical testbed looks like. It is fully self-contained and mobile. Devices under test are completely isolated from external interference and from each other. This complete isolation, along with the anechoic nature of the chambers, provides for a well-controlled and fully repeatable test environment. The RF from the access point, in the bottom chamber, connected over coaxial cable, travels up through the multipath emulator, then through quad attend variable attenuators to the device under test. In this case, we have a 4x4 MIMO link coupling into the top chamber, with the final link to the device under test being over-the-air coupling. This chart will be consolidated by the throughput script into a single data point. Looking at the chart, it appears that the steady-state throughput is around 590 megabits per second. But you can see that there is a lower throughput rate at the beginning of the run. MIMO devices always implement a training period to optimize the use of the channel based on conditions. You can see in this chart that the throughput during the training period is vastly different from that seen on steady state, under 300 megabits per second in this case. We have roughly 8 seconds of lower throughput that will completely skew our steady state average. The octoScope throughput script removes this extraneous data for each of the data points in a test run. The number of points in a particular test run depends on the number of attenuation steps specified in the throughput script. At each point we can specify how long we transmit data and whether to introduce device rotation during the test. So, for example, the script can rotate the turntable over the duration of one test point, thus averaging the performance over the device orientation. This will result in a throughput plot versus range and attenuation, as shown here. Polar plots are also useful in understanding device performance. In this case, we rotate the device to distinct orientations, in this example every 30 degrees. At each of those points, we go through the number of attenuation steps programmed to get the plot shown here. It's thus easy to discover any issues with an antenna. In this particular example, the device we measured had a piece of metal blocking the antenna, and the results clearly show the resulting degradation in performance. Each point on a polar plot is an attenuation-rotation combination. A more detailed orientation plot is shown here. This plot reflects 12 attenuation values at each 15-degree rotation step. The fine resolution shown here was produced by a run of about 5 hours. Manually collecting this data in a completely repeatable fashion would be time-consuming, labor-intensive, and quite error-prone. The octoScope throughput testbed described here is currently being used by smallnetbuilder.com for benchmarking. Their website features the latest and greatest access points being evaluated and compared using the octoScope testbed. Smallnetbuilder.com publishes comparative functional and performance data for many current access points. This is made possible by the most consistent and repeatable testbed available, octoScope's octoBox testbed. octoBox has many useful building blocks. For example, iGen is an interference generator useful for both free space and isolated testing and mounts easily on the octoBox as shown. iGen can generate a wide variety of interference during a test. It's also possible to monitor the behavior of over-the-air traffic during a test. This can be done with a commercial USB sniffer attached to one of the filtered USB ports, completely isolating the sniffer from any external interference. Filtered ports are provided on the back of octoBox for gigabit Ethernet connections, USB, filtered audio, HDMI, and fiber connections, all while keeping the environment completely isolated from external RF signals. A very important element of the testbed is the Multipath Emulator, or MPE. The MPE emulates multipath that occurs in the over-the-air environment. Multipath is caused by signals reflecting off of objects in both indoor and outdoor locations. Each reflection generally results in a reduction in energy, with longer distances and a greater number of reflections resulting in significant signal degradation. Standards bodies, such as the IEEE and others, model multipath as groups of clusters of reflections that are similar in angle of arrival and delay. One way to look at multipath model is the power delay profile. The power delay profile shows the power level of reflected signals as a function of excess delay. This is also known as the impulse response of the channel. Octoscope's MPE models the multipath behavior of a typical house, implementing the IEEE 802.11 Model B. This indoor model, originally defined by IEEE 802.11, is also useful for testing Wi-Fi, Bluetooth, and 802.15 technologies like Zigbee. The Model B profile is a two-cluster model with a power delay profile as shown in this diagram. The Octoscope Throughput testbed is a fully self-contained, isolated, mobile, repeatable, and compact solution for wireless performance evaluation. It can emulate the always-present artifacts and impairments seen by real-world wireless communication systems, including multipath, fading, and interference from a wide variety of sources. And it's fully automated so that throughput and interference scenarios can be explored at will, enabling a comprehensive and cost-effective examination of the behavior of your devices under a wide variety of challenging conditions.